So our next speaker is Dr. Ryan Zeigler, curator of Apollo samples at NASA Johnson, and he's going to talk on NASA and the Moon from Apollo to Artemis. Ryan.
Thank you. And thank you all for having me. This is really exciting. I should warn you right off that my title's kind of a lie, certainly misleading. I mean, I work for the government, so that shouldn't be surprising. But this talk is going to mostly be about Apollo, and there'll be a little about Artemis, and that'll be obvious when I get to the part about Artemis, which is still evolving rapidly. I'm the Apollo sample curator at Johnson Space Center, and at Johnson Space Center we curate all of NASA's astromaterials. So if it's a rock from outer space, it's our job to take care of it. So this is sort of our one-slide summary of everything we do, and on the top line you can see the 8 collections that we have that we're currently taking care of, where the Apollo samples are the first and obviously the best, although as the Apollo curator I'm required contractually to say that. Best collection we have, and really it's all I'm going to have time to talk about today, but we really have quite a range in samples. So the Apollo samples we'll talk in lots of detail about, and then there have been teams of scientists going to Antarctica since the late 1970s collecting meteorites, and these come from asteroids and planetary bodies throughout the solar system. We have cosmic dust samples, so NASA has, we're not supposed to call them spy planes, certainly not on things that are being recorded, high altitude reconnaissance aircraft where they fly up into the stratosphere and collect all the dust, and about 10% of that turns out to be mostly cometary material that's drifting down through our atmosphere, and so it's sort of free sample collection from comets. And then we've actually gone to a comet and flown through the tail of a comet, the coma of Comet Build 2, and brought back samples that were directly collected from there. I skipped Genesis. Obviously, we went out and collected the solar wind sitting at the Earth Sun L1. And then most recently, we've gotten about 10% of the samples from the Hayabusa mission, which is a JAXA-led, or JAXA mission, to collect material off of an asteroid. So, our job is sort of 2 parts. We're trying to maximize the science we get out of these samples, and we provide them to scientists around the world to do just that. But we're also trying to preserve the samples for future generations. And since the Apollo samples are now 50 years old and we're still studying them, we feel like we're doing a pretty decent job of that. We also have to get ready for what's coming. We've had, like I said, 7 or 8, depending on how you want to count, collections that we've accumulated over the years. But we have 2 more that are going to be back in the next few years. There's the Hayabusa 2 and OSIRIS-REx missions that are coming back from asteroids, as well as on-the-books missions from the Moon, Phobos, Mars, and hopefully a comet again. So it's always good to show where you come from. And so here's my office at Johnson Space Center. Everyone doesn't have this photo? I don't know why you're having trouble finding our building. We got them to point the plane right at it. So here are our laboratories, this suite. And it's a great picture, actually, because the original home for the Apollo samples is actually right here. This is the Lunar Receiving Lab, which was the home for the samples till about 1972, when they realized that they didn't need to be in a quarantine facility. And so they built us a new lab in here from 72 to 76. 78, and then they built this custom-built building for us in 1978. And so you can see that our samples are actually spread, our collections are spread around the 3 buildings we have here, and then everything in blue is what we're building now. And so be glad we're doing this talk here and not in my building, because 1/3 of our building is being jackhammered right now, and it's really an unpleasant place to work for the next 2 years. Right, that's mostly for fun. So Apollo, why is it important? I mean, for me, and I realize I'm biased, that landing astronauts on the moon was the seminal moment of the 20th century and really the crowning technological achievement, period. And I'm happy to argue with you about that and explain why you're wrong if you disagree with me. So it took a huge commitment. It was, in modern money, it was about $125 billion. It was a significant portion of the U.S. budget at the time. It was 250,000 people working on it. Something like 10,000 different companies worked on it over the lifetime of it. So it really took a nationwide commitment to do this. But we'll talk a little bit later about how this actually, it seems like an obscene amount of money. It is an obscene amount of money. But really the amount of return they got from the samples and from just the missions in general really were good. I mean, there are many legacies to the Apollo program, and historical, cultural, technological, and I've underlined scientific, not because it's necessarily the most important, because it's arguably the only one I'm qualified to talk to you about, so I figured we'd focus on that. So I'd like to talk to you a little bit about the most important scientific advances most important things we've learned from the Apollo samples over the last 50 years, and really not just what it taught us about the moon, because that's sort of obvious. We're going to learn a lot about the moon from the lunar samples, but really we've learned about a lot of other planetary bodies in our solar system as well, so I'd like to highlight that. And then we'll talk a little bit about what we're going to get out of the Apollo samples, why we're still studying them after 50 years, and then why we need to go back and get some more. So this is my favorite picture of the moon, and you're probably sitting there thinking, I've seen better pictures of the moon. Now, what makes this one really important is the date that it was taken and where it was taken from. So this was actually taken out the window by the Apollo 11 astronauts after they had landed and were on their way back, which is why the orientation's all goofed up and you're seeing parts of the moon you really shouldn't be able to see from Earth. There were many things that set the Apollo program apart, and what sets it apart from our collections is that it was collected by people. So we had the Saturn V rocket. It was the largest and most powerful rocket ever, and it really let them bring a lot of mass to the moon and a lot of mass back from the moon. But it was the astronauts that really set it apart. Now, if it turns out that astronauts are really useful. And if you don't believe me, ask an astronaut, and they'll tell you. It's funny, at least you guys laugh. When I tell that joke to the astronauts, they just get mad at me. Right. So no, the real reason I'm showing this is A, to make my only joke I have, and B, to show all the different things that the astronauts enabled to be done on the mission. And so if you were designing a robotic mission, and we've done this, and many space agencies have done this, the robot usually focuses on one thing. It's a geophysical robot. It's a sample collection robot. They're going to go collect samples from Mars. And Mars 2020 is the first in that series of rovers to do it. And it's going to go and drill and collect it. And another one's going to go and bring them all together. And then another one's going to go and launch it back to Earth. So you can make robotic missions do anything you want, but they're usually highly specialized. And if you want to make a robot that does everything, it's really expensive and really technologically challenging, and it takes a lot of mass. So the astronauts could do everything from drill a 3-meter core, take a 60-centimeter drive tube, collect samples with a rake, pick up samples off the ground. That one was pretty easy. But deploy geophysical networks, drive around in dune buggies, and apparently drink coffee, which is important even when you're collecting on the moon. And I make that joke, but that's actually a really important sample. That is one of the special environmental sample containers, and we still have that as one of our unopened samples. So it had a metal knife-edge seal, and they were able to seal it under vacuum on the moon, and it's remained that way ever since. And it was a really technically challenging thing to do through a spacesuit. And they took 3 of them on the Apollo 15 mission. That's from Apollo 12, unfortunately, and only 2 of them ended up okay. And we still have 1 left. So here's a more modern view of the moon. This is from the Lunar Reconnaissance Orbiter camera, and I've highlighted the Apollo sampling locations in red. And so if we talk about the Apollo samples, if we wanted to summarize them in one word, which I just used 20 words to get to, you would do that with diversity. So there were 842 pounds, 382 kilograms, 842 pounds of moon rocks collected from the 6 locations. And these are some of the most well-known samples that were brought back, so the rock stars of the rock world, if you will. And if you're looking at the moon, you'll see that there are the heavily cratered highlands, the bright parts, and then the basaltic marea. And so the anorthosites in a simplistic world, these igneous rocks make up the highlands, and these igneous rocks make up the marea. And then we have a few sort of rare igneous samples that form deep within the moon, and these are the ones we like to talk about. It turns out the most common rock type brought back from the moon is something like this, which is a regolith breccia, which is a smashed up rock made of pieces of other rock. Earth is very well protected with our atmosphere. We don't get a lot of small to medium-sized impacts. You know, every grain of sand doesn't create an impact crater. On the moon, it does. And so we have about 100 kilograms of these total. And out of the total mass that was brought back, we have about 30% of it is soil. And you normally think of soil as this fine-grained talcum powder, and that's true. But mixed within it, about 10% of it is greater than 1 millimeter in size, and each one of those rocks has an important story to tell, and we still have tens of thousands of those small rocks that have never been looked at. And then finally, we had the core samples, which gave us the vertical stratigraphy within the moon. And so I think I've already said most of this, but what really summarizes what the Apollo samples taught us about the moon is that they had a very restricted area. There was only 6 locations from the moon, but exquisite geologic context. So they had lots of pictures and lots of information to go with the rocks and really made them more useful. To contrast that, we now have over 200 lunar meteorites, pieces of the moon blasted off the surface by impacts that have fallen to Earth and been picked up. Those give us a wonderful global average of the surface of the moon, but we have no idea where on the moon they came from, certainly not with any level of detail. And so the two of those are actually very complementary. And so in going back with Artemis here and getting new samples from another known location will be really important. So this should be a short slide. Are they still useful after 50 years? And yes. It turns out, and it's a little bit of self-serving for me to say this, it's because we've taken good care of them. And I'm using we very liberally. I'm the curator now, but for the 45 years before me, there were 8 or 9 other curators, depending on how you want to count, and many dozens of people who've worked in the lab, and they've spent their lives, their careers rather, no one's been lost yet, to protect the samples. And so our job is to keep them as much like they were on the moon as possible, and obviously we can't do that exactly. The 10 to the minus 13 torr on the surface of vacuum on the surface of the moon, we can't quite do that in the laboratory, at least not on the scale we do. But we store them inside dry nitrogen cabinets. The cabinets themselves are made out of a certain type of stainless steel. Our tools are made out of stainless steel, aluminum, Teflon, and that's really the only things we let around the samples. And that has enabled, over the last 50 years, an incredible diverse number of studies about the samples. And just to give you an idea of how many have been studied, and also because I wanted to at least make one chart for my own talk, and it's a log plot, so it's very fancy for a geologist. So we just had our 32nd 100, almost our 32nd 100 requests for the samples. So we've been averaging a little over 60 requests for samples. We have handed out about 50,000 samples. You'd think I'd know exactly how many samples we've handed out. Turns out the first few decades are not really digitized yet. We have a record, we just haven't put it all in the computer yet, so we're working on that. But it's at least 50,000, and unless you think we did all of those in the first few years, here's all the digitized data I have going back to 1984, and we averaged about 1,000 samples a year that we were handing out, and we're almost back up to that, and the number of requests here is in the, 60, 70, 80. There was this sort of what we call the lean years, the Mars years, where life was found on Mars, that we saw a downturn, but we fought through that, and all right, sorry. No more Mars jokes, sorry. Again, we're recording this, right? Yeah. So, you're right. And I mentioned that scientists around the world have the samples. And so right now there are about 10,000 Apollo samples on loan to about 125 investigators in 16 countries. And I made this small enough that you can't read it, but about 60% of the samples go to the US, but obviously that means 40% of them don't. And so the largest single country, the largest number of PIs in any other country is right here in the UK. And so I did add this up before I came. There are 12 lunar PIs in the UK right now, and they're spread across 7 institutions, which I've listed here. And I had the privilege of listening to Grenville Turner, who was one of the original lunar PIs, give a talk earlier today, and he said something that I think is a coincidence, but was really interesting. There were about 130 or so lunar PIs, principal investigators, who were pre-approved to work with Apollo 11 samples. And again, they were all over the world, and there were between 12 and 14 in the UK. And so we currently have the same number of PIs as we did originally, and about the same proportion of them are right here in the UK. And so that's probably a coincidence. I don't have the data for all the years in between, but certainly there's been a lot of work going on here. So, trying to summarize those 3,200 studies onto one slide, and this is what I came up with. So, luckily, I don't think there are that many people here who study moon rock, so there'll be fewer offended people. We aren't going to go through all of these in detail because that's a longer talk and I don't want to get tackled. Again, I really want to try to highlight not just what these taught us about the moon, but what they taught us about the solar system as a whole. So why don't we start with this one? This is that the moon formed through a giant impact. So there's numerous lines of evidence, mostly isotopic, that suggest that the Apollo samples and that the moon and the Earth used to be part of the same body, and that it was the moon formed through a giant impact. Now the details of that are under debate still. It could be this is sort of a view of the standard model, I think they're calling it now, where something the size of Mars slammed into the Earth a few tens of millions of years after the Earth formed, and the moon formed from the ring of debris that came from that. Some of the newer models have the entirely still have an impact, but then there's a cloud of vapor, something called the Sinestra model, which I didn't have a good picture of. The details of it I don't care about. I just like that people study our samples, and that in order to figure out exactly how the moon formed, they're going to need samples in order to do that. And a byproduct of that, or related to that, is that the moon had an ocean of magma. So it wasn't, the entire moon was molten to a depth of, all right, here's where the fight starts, but 1,000 kilometers deep, 600 kilometers deep. So you've got this ocean of magma, and just like any lava flow, it starts to cool off, and then the first few minerals to crystallize out are olivine and pyroxene, which are iron-rich. They sink into the interior of the moon, and then the next one that comes out usually is plagioclase, which is iron poor, and it floats to the surface, and we have anorthosites, and then impacts took over, and it evolved from there. Now, this is obviously telling us how the Earth-Moon system formed, but it's also how this information gives us the best understanding of how Venus and Mars and other planetary bodies formed as well. I mean, they're just ramping up to argue about whether Mars has a magma ocean or not. There's new papers coming out that are going to call that into question, and they're going to rely on lunar data as one of the checks for that. We have impacts on the moon. So this is the Oriental Impact Basin. It's about 1,000 kilometers across. There are 40 or 40-ish basins of this size on the moon, and we know their relative age. You can tell by how the ejecta from them lay on top of each other. You can put them from oldest to youngest. There seems to be, these large impact basins are important because they have samples like this. They're called impact melt breccias. They form from molten rock, but the molten rock didn't form from a normal geologic process. It's from the kinetic energy of the impactor. If you look at the age of many of these samples, including the age of these type of samples within breccias, they tend to cluster around 3.9 billion years old. Now, that might be a selection effect because we have relatively few collections. But right now, I still think most lunar scientists believe there's something called a lunar cataclysm, where there was a cataclysmic event in the inner solar system where a bunch of large impactors to make impacts this big slammed into the moon and the other terrestrial planets. Now that's a problem if you're trying to do solar system evolution models where you don't really have a group of impactors that should be swinging around the solar system 600 million years after it formed under the normal models. And so that, in part, led to new models for solar system formation, like the Grand Tack model or the Nice model. And this is really not something I want to talk about in front of you guys, because you all know more about it than me. But again, I don't really care what the right answer is. I care that the Apollo samples and that samples in general are going to play an important part in figuring out whatever that answer ends up being. And it won't just be the Apollo samples, it'll be the meteorites and the different type of asteroid samples we get back. And all of those are going to be required along with the model results in order to make sure that they get the right answer. Here, you can see the Apollo 11 landing site. So I just talked about the really big impacts, the ones that are hundreds or many hundreds of kilometers across. But obviously, we have impacts from that size all the way down to sub-millimeter, a few microns across. So here's the Apollo 11 landing site. And you can see the basalt in the top right, and you can see a little bit of the highlands in the bottom left. And so this brings us to something called crater counting, where in a relative sense, crater counting is easy. If you look at don't tell the people who do it, I said that, but if you look at this surface, this is obviously younger than this surface because this has been around longer and a lot more craters, things have slammed into it. And so as a relative age dating technique, it's really good. Now you can't really make it out on here, but there are actually basalt flows in here, and there's different units within the basalt. And if you do detailed counting on those units, you can actually see that there's tens of millions of year age differences between some of them. Even, that's about the best resolution they have. Now this is important because we have samples back from known locations on the moon, but we don't on Mars, we don't on any other planetary body. So if you want to do crater counting on the moon, on Mars, you can in a relative sense, but if you want to try to put any absolute ages, I kind of forgot. Here's the basalt from the surface. Yep, sorry. And because we've dated this basalt, because we know the size of the basalt flow, we counted the number of craters. I'm being very liberal with we. I did none of this. You have an idea of how many craters per million or billion years you get. And that's what this little tiny graph is showing you, that in time before present, these are different Apollo landing sites where they've dated the rocks, done the crater counting, and you get what's called a crater counting curve, where if you take any surface on the moon, you count the number of craters, you know how big it is, you can get an absolute age for it. You can then take that exact model and move it to Mars or Venus or Mercury. The farther you get from the moon, the more the numbers, the bigger the error bars get, but it's still the only way we have right now to put absolute ages for like the Hesperian terrain on Mars or the Caloris impact basin on Mercury. So. And here you can see where they've done it from the moon, where the oldest craters are over here that are, I'm sorry, the oldest basalt flows are over here, about 4 billion years old. But the age of volcanism on the moon ran as young as 1 billion years. And that's really, really surprising based on the size of the planet. We also, obviously sample return missions are the best type of missions, but there are other useful missions out there as well, like the remote sensing missions. Here you can see, this is from data from the Lunar Prospector mission, which mapped thorium concentrations at the surface of the moon. So it just flew in orbit, it counted the gamma rays coming off the surface, it knows those gamma rays came from thorium, and it turned it into absolute concentrations of between 1 and 12 parts per million for the entire surface of the moon. But they were doing this on first principles, and they were doing this on the fundamentals of how gamma ray generation occurs, but then it occurred to them that they actually had 6 landing sites on the moon where they knew the composition. And so they were able to take the orbital data from Lunar Prospector and compare it to the ground truth, the actual data from the soils on the Apollo mission, and able to fine-tune their measurement, and it actually made a big change in the concentration of this in the background. And this has been true for any of the missions. Grail, that did gravity, it used Apollo samples and their density as a ground truth. So every orbital mission uses the ground truth, important. And then finally, and the one I'm most nervous to talk about here, is that the Apollo samples are actually useful beyond our solar system as well. And there's a couple ways, one of which is exoplanet spectroscopy. One of the largest sources of error in that is actually reflected moonlight. So understanding the characteristics of the light that reflects off the moon that interferes with this type of spectroscopy is important, and we've actually allocated samples for people to study that. And the other one is galactic cosmic ray history. Now, our solar system obviously orbits around the center of the galaxy, and as it does so, the background galactic cosmic ray exposure changes. And it could change significantly depending on whether there happens to be a supernova or any other big event that produces a lot of radiation as we go through. Now on Earth, this is largely mitigated by our atmosphere, and we don't have you can't use the geologic record on Earth to measure this. On the moon, you can. And for the Apollo samples, we have a few samples that are useful for this, especially the deep cores. But this is a case where when we go back to get new samples, this should be something we target, where we try to get a stratigraphy of soil, particularly soils in between layers of basalts, that will allow us to understand the local radiation environment for our entire solar system. Yeah, not used to talking about anything other than the solar system. Right, so why are we still studying the Apollo samples? What are the most common things we're still looking at? Well, there's 2 things really. So we have all these regolith breccias I mentioned, and we have all this soil. And mixed within it, especially if we start with the regolith breccias, it used to be we would take our regolith breccias, we'd put them on a bandsaw, and we'd slice it like bread. And then we would take those slices and we would see what we saw. And that wasn't a very efficient way to do it. It wasn't great for the samples. Well, now we have a high-energy X-ray CT scanner. So just like you get a CT scan or an X-ray of your arm, we can now X-ray the entire rock. And we can map out where the different rock types are within these breccias. And each one of those breccias, each one of those clasts can tell a story about the moon. This is an Apollo 16 sample, which is iron poor, and this is a basalt clast. And there's only one basalt clast known at the Apollo 16 site, and this is it. Now we cheated a little because I knew this was there because it was on the outside. But we now know how big it is, and we know that there aren't any more in there, and that's important. And so there's about 100 kilograms of this that we're going to start systematically going through and mapping these out, and then we'll be able to advertise. And these are essentially new samples to science. And then here's the soil, and here's a picture of the Apollo 11 regolith. Now we've sieved out the less than 1 millimeter stuff. We've cleaned it up. I ran it through acetone to make a pretty picture. But within this one soil, you can see 5 or 6 different rock types. Interestingly enough, John Wood studied this exact same sample in 1969 when they first came back, found these anorthosites, and came up with the magma ocean model for the moon. So that's how useful these can be. And so expanding this to other sites and trying to find that 1%, the exotic material that came from distances from the site, will be important. We also have a few types of samples that weren't previously open. We had 2,196 samples. So I have 6 samples that no one has ever studied. And we're about to open 3 of them. One of them was sealed under vacuum on the moon, And that's going to get opened. They're going to measure the gas that's inside. That's why they waited, so mass spectrometers to be better to do it. They have a paired unsealed sample that they're going to do. We also have some frozen and some samples that were open and stored in helium as opposed to nitrogen. So all of these are going to be made available. The work hasn't started yet. It's going to start soon, but since this is being recorded, I'm not going to say when. In the next couple months. And there were 9 groups of scientists, about 50 scientists total that were collected. Here you can see their PIs. Here you can see the PIs. None of them are based outside the United States because NASA's paying for it and it's kind of hard to send money overseas. But 2 of them are recent PhD graduates both from the University of Manchester and from the Open University. So there's that. All right, do we need more samples? Yes, I went to the Lunar Planetary Science Conference a few months ago, and this was the list of things that people wanted. This was their shopping list. Every time I'd watch a talk, they'd be, oh, we're gonna need to know more about the mantle. We need more mantle rocks. And Ryan, get on that. I'm like, yeah, that's how it works. I decide where NASA goes. But I mean, it was this huge list of places, and here's the 3 places I want us to go. But again, like I said, I don't get to decide that. But NASA is getting ready to go back to the moon. I mean, this is the major push for NASA over the next 4 years. It's called Artemis, and they are going to send humans back to the moon in 2024. And they are committed to this, and this is really my only slide on it. And we are still in the formation phase. We are giving them very technical feedback on it in terms of the type of samples they should bring back and where the samples should come back from. And the short answer is the samples are coming back from the South Pole. Now, this has been said publicly. I don't think it's been shown exactly, but they're going to land somewhere right near the South Pole, and there's a couple of reasons for that. One, the illumination conditions are favorable. Hardest part about having people on the moon long term is surviving the lunar night. 14 days with no sun, no power. That's a challenge. So some of these, because of the inclination of the moon relative to the ecliptic is so small, some of these areas along the rim of Shackleton Crater have daylight for about 96 or 7% of the time. So you have a constant supply of solar power. You also have these giant craters like Shackleton, or these very deep craters like Shackleton, which for the same reason are permanently shadowed and therefore are extremely cold and are a cold sink for volatiles. And so there is abundant evidence that there is water ice of some form inside these craters. Now, how you get down the 7-kilometer high scarp into Shackleton Crater, well, we're working on that part. But there are smaller permanently shadowed craters not shown on this scale that should be accessible. And then there's also this, which is the South Pole Basin, which is the largest, oldest, deepest basin on the moon. And one of the places you would get good ejecta from this will be at the South Pole, right on the rim of it. So when people want the lunar mantle, this is actually probably a pretty good place to go. So with that, I'll just leave my summary slide up and take a few questions if I have time.
Well, thank you very much. That was a really excellent talk. It's open now for questions. Yes, Debbie.
Thank you very much for a very interesting talk. Just a couple of quick questions. The first one is, looking forwards, we've seen the Changi mission go to the far side of the moon.
Yep.
In terms of reciprocity, and I know there's a political aspect to this, will you, how you determine who you'll share your samples with and whether or not they'd be prepared, for example, China, to share them with you?
Yeah, that's a couple levels of government above me, like the State Department. No. I mean, we traded samples with the Soviet Union in 1972 and then again in 1978. The scientific community it would be very excited to do that. There are U.S. laws about agreements between Chinese institutions and U.S. institutions that we would like to go away, but again, that's we being the scientific community, not me speaking for NASA. No. So I mean, that is a complication.
So it's still an
opportunity. Being fed to the White House.
Yeah. No, that's
it's still a potential opportunity. And a very quick second question: Apollo 17, the last mission with Harrison Schmitt, was the only geologist to go to the moon and walk on the moon. Was it a tremendous boost in terms of the samples he selected?
It certainly was. I mean, a lot of the astronauts, and certainly astronauts on every mission, were avid geologists, even if they were amateur geologists. Jack was obviously the only professional. Jack's still involved with the samples. He'll be there when we open the sample in a few months. So maybe not right. He's not going to be the one cracking it open, although I don't think we've broken the news to him. So hopefully he's watching. No, but I mean, he has played an active part, and his samples really were special, and Gene's too. Gene, certainly.
Thank you so much.
Super. One more question. Yes, at the back there, please.
Okay, so if my memory serves me right, I was about 16 when Apollo 11 happened, and in fact I went to Sheffield Museum to see a little phial of black substance. But I also remember, if I'm correct, quite a few were given away as diplomatic presents, and so the question is, have any of them ever come back, and how many were given away?
So I don't have the exact number. About 120. Every country that was a country in 1969 and in 1972 were given a goodwill sample from the Apollo 11 and then again from the Apollo 17 mission. And when I say everyone, I mean Cuba in 1972 got a goodwill sample, and we didn't have very good relationship with them at the time. They were out and out gifts. We don't track them. We don't keep track of them. One or two has turned up and been recovered in various ways and returned to the country it came from. But we don't actively do that. We just help when they ask. Is that a diplomatic answer?
Ryan, that was a fantastic talk, Ryan.
Okay.
Thank you very much indeed.